Hi guys, how's it going? Hope you're looking after yourselves and being kind to each other. It's me, Terry, here with another Strength of Engineering Materials video lecture. And this week we're looking at transformation of 3D stress and also theories of static failure and strength-based design. Again, I'll be using JC's lecture notes, but I've also added a few of my own into the slides for this one. Hopefully they're helpful for you. Also, I've kept my head up in the corner here. Had a couple of comments from students on the previous videos saying that they like to see my head up in the corner explaining things as I was going along. So I'll continue to do that for now. The notes on UTSOnline should be available for you. If you got them previously, because I've added some new slides in here, you might want to download those again. So just check that you've got the slides that match up with these videos. Okay, so let's get into it. So again, I'm going to split it up into two videos. So the first part will be transformation of 3D stress. So this continues on from the 2D stress that we looked at last time. Don't worry, it's not quite as complicated as it might sound. And hopefully I can simplify it enough for you to understand the concept, if not all of the details. And then we'll go and look at theories of static failure and strength-based design in the next video. Okay, so objectives of this first part is to determine the principal strains and principal stresses in the 3D case, and to determine the absolute maximum shear stress, because what we calculated previously in the 2D case was just the maximum in that particular plane, and as we'll see, the out of plane shear stress can be much greater. So this is a slide from last week's lectures. I'm not going to go through that. We'll cover some of this as we go through the 3D Mohrs Circle, but it's here for your reference again. And also here, these are the details that I went through in the video lecture last week. So you can go back and look at and listen to that video again. And again, I'll go through some of this in today's lecture. So up until now, we've looked at a 2D state of stress, and particularly a plane state of stress where all of the stress components are contained in a single plane. But in general, we can have a normal stress and two shear stresses on each of the faces of our element representing the point at which we're calculating stress. So in total, we have 6 independent stress components, 3 normal stresses, so stress X, stress Y, and stress in the Z direction, and 3 normal stresses, shear stress XY, shear stress YZ, and shear stress ZX. Okay, and from that we can get to a principal state of stress like we did in 2D, but this time we've got a 3-dimensional state of principal stress. Okay, so transformation of 3D stress using Mohrs Circle. The 3 planes that we have here can be represented by 3 Mohrs circles. So previously we had 1 Mohrs circle to represent the AB or the XY plane that we started with, but we can also have 2 other circles, one that represents the AC plane and also one that represents the BC plane. Okay, and that looks something like this. So on Mohrs Circle, so here for example, point stress A, we have no shear stress, so its coordinates on the Mohrs Circle axes, horizontal axis is the normal stress, vertical axis is shear stress, so that will be just stress A and 0 for the shear stress. So that's that point there. Stress B will be this one, and stress C will be this one here. Okay, and they're principal stresses because we can see, or because we know that the shear stress on each of those faces is 0. And when we're looking for the the largest shear stress, or the maximum absolute shear stress, which is important when we look at failure criteria, because as you'll see coming up in the next video, ductile materials fail on planes of maximum shear. So we need to know this absolute maximum shear stress, not just the maximum shear stress in the plane that we happen to start our calculations in. Okay, so that's just the radius of the biggest circle, and you can see that the maximum shear stress will be half the maximum stress minus the minimum stress. Okay, so even though we have a general state of stress in 3D, we can usually start with a simpler state of stress, such as we did with the plane stress condition that we've looked at so far. Okay, so here's our general state of stress. The plane stress condition is that all of our stresses are contained in a single plane. Okay, so we've got normal stress in the XY plane, normal stress in the X direction in the XY plane, and shear stresses in the XY plane. And we've become familiar with looking at the two-dimensional view. So what we're doing here is looking down from the top, or down the Z-axis at this element, to see our stresses in 2D. Okay. We can also start with a simplified state of stress where it's like plane stress, but we have a stress in the Z direction, so a normal stress in the Z direction. Okay, and we can also deal with that as well. And fortunately, 90%, even more of the problems that we need to deal with fall into the plane stress case, or the case where we have a stress in the Z direction, but it's still a principal axis. Okay, so this is just my notes that I've inserted here. So showing you the case where you've got almost plane stress, but we've got an addition of the normal stress in the Z direction here. Okay, and as I said before, we can look at the first Mohrs circle as we've done so far for 2D, so just in the XY plane. So we're familiar with finding the principal stresses and transformation in this 2D XY plane, and then our further two Mohrs circles can be drawn by looking at the ZX or the ZA plane and the YZ plane. Sorry, not the YZ, it will be the principal BZ plane. Anyway, you'll see that in a second. All right, so here we have the Mohrs circle. So if we start with our normal way of doing things that we've done last week, so there's the revision of last week's work. So we have our stress pair here, stress in the X direction, or normal stress in the X direction, and a shear stress. So that will be plotted down here. Okay, so stress in the X, normal stress, and the shear stress is going anti-clockwise, so it will be down here. Then we have this stress pair, stress in the Y direction. It's a normal stress and its associated shear stress, so that will be plotted here. And we can also calculate the center of the circle from the average stress, so just stress X plus stress Y divided by 2. And that gives us our Mohrs circle in 2D that we've done before. Okay, so then we can work out the radius if we need to for the in-plane shear stress. Okay, so now we can start to take into account our three-dimensional states of stress. So in this general problem, we have a normal stress in the Z direction. Okay, so there's no shear stress on this face, so this will be stress Z for the horizontal axis, and shear stress is 0, so that gets plotted down here. So that will be that point there. Once we've done that, we can then draw our two other Mohrs circles to represent the other two planes. I think I might have done something else first. So yeah, so before we do that, we need to rotate this XY state of stress into our principal stresses in that plane. So principal stress A and principal stress B in this XY plane. So let's do that. So this is where we get to. Okay, so we've rotated from the X-axis around to our principal axis anti-clockwise on Mohrs circle. So we rotate from X around anti-clockwise half that angle to get to our principal stress axis. Okay, so this first circle here, circle 1, represents transformation of stress in the XY or the AB plane. So we have AB is coincident with the XY plane. We just rotated the X-axis to the A axis and the Y-axis to the B axis. Now we can start to look at the other two circles. So circle 2, so this one here, represents transformation of stress in the AC plane. Okay, so we've got stress A here, right there, and stress C out here. So we're transformation of stress in this AC plane here. Okay, so there's stress A and stress B, right, that one here. Circle 3 represents transformation in this plane here, BC. Okay, so rotating about this A axis. Okay, hope that makes sense for you. Let's jump to the next slide here. So once we've done this, we can now recognize that the absolute maximum shear stress is now in a different plane to this original one that we started in. Okay, so we've done our stress equals my upon I calculation, stress equals TR upon J for torsion, and done our drawn our stress element, and then calculated our principal stresses using Mohrs Circle. Okay? And up until now, we would have just taken this here as our maximum in-plane shear stress. But now, because we're considering everything in 3D, we've got this maximum shear stress here in a different plane. Okay, so what I've just shown here, I've just created a SolidWorks model where I've got the original stress element in see-through box here, and the red box represents, or the red cube represents, the principal stress orientation. Okay, so the A axis and the B axis for those principal stresses, and we've got our C axis coming out this way. Unfortunately, SolidWorks puts the positive direction out here. I couldn't work out how to change that, but you can see the positive Z is out this way. Okay, so the absolute maximum shear stress plane in this case is at 45 degrees to the AB and BC planes. Okay, so let's have a look at that, what that looks like. So what we've done here, or what I've done here, is again to create a SolidWorks model. It may be a little difficult to see. Don't worry too much if you don't get the orientation and location of the maximum shear stress plane correctly. That's of lesser importance than actually realizing that there is a maximum shear stress out of plane and being able to calculate this value. If you can get this, great. If you can't, don't worry too much about it. But I thought I'd put it in here just to show you. So we've got the AB plane here and the BC or the BZ plane, and this plane here is at 45 degrees to those two planes. Okay, because on here we've got a 90 degrees on Mohrs Circle. Okay, so I've just got some more images here to try and illustrate that. Okay, so here's our rotated element in the principal orientations. So looking at the maximum in-plane shear stress, right, so this is this one here. What we're doing here, so this is X and Y axis. So we're now looking down at the top, or actually probably from the sorry, what are we looking at? Oh, sorry. Yeah, we're looking from the Z axis here. So looking down the Z axis at this face, our 45 degrees here is between A axis and the B axis, right? So that is going to be here, right? 45 degrees. So looking down this Z axis, we can see that maximum shear plane. Okay, so this is what we've done up until now. So I've just rotated that a little bit so you can see that shear plane there. Okay, so at 45 degrees to the AC plane and the BC plane. So our absolute maximum shear plane, again, I've looked at this in 2D, so we're looking at the AC axis, so we're now looking down the B axis at this element, okay? And our maximum shear plane is at 45 degrees to the, which one was it? The AB plane and the BC plane. Okay, so we can see that there. And again, if we rotate that a little bit so you can see it in 3D, there's our plane of maximum shear stress. Okay, again, as I said, don't stress out too much, no pun intended, whether if you can't quite see these orientations, that's not the most important thing. The most important thing is to be able to calculate this absolute maximum shear stress and to realize that it exists outside of this original 2D plane that we looked at originally. I've also included here just some out of plane shear failure. So these are pipes or pressure vessels, and the stress state, as you'll see in a week or two when you do pressure vessels, is you have a longitudinal normal stress and a hoop normal stress, no shear stress in this orientation. So when we get to yield, and when you look at the failure criteria in the next video, you'll see that the maximum shear stress occurs at 45 degrees, which we've just seen. And you may be able to see in these pictures that even though that this is torn open this way, across and down the length of the pipe, because the hoop stress is twice the longitudinal stress, so it opens up like this, but the actual failure surface in here is roughly 45 degrees. You might be able to see it on this one down here and here, and also here. Usually when I teach this subject, I've got an actual physical specimen that I can hand around, and you can see that a little bit more clearly. Yeah, so we'll look at this in a bit more detail later. Just try and remember this practical application when we get to looking at the failure criteria later on. All right, so back to JC's notes. So here's just some excerpts out of the textbook, looking at the case of plane stress, where stress in the Z direction equals 0. So even though the stress in the Z direction is 0, doesn't mean we could ignore it. Right? So when we're looking at the 3D state of stress, because when we look at the 3D Mohrs circle, if we have both of our principal stresses in the original XY plane positive, then we have a 0 normal stress in the Z direction. We still have this point here, so we can still draw our 3 Mohrs circles. So we still have this larger Mohrs circle that gives us our absolute maximum shear stress. Okay, so these are just some more excerpts out of the textbook, showing you that you can find the shear stresses, or the maximum shear stresses in each of the 3 planes. Okay, it's of limited practical application. The main one to be concerned about is that you get the absolute maximum. Okay, and also showing that you can draw the stress element on for the orientation where you have maximum shear stress for each of the different planes, and in each of the different planes you have an associated average normal stress. Okay, so the absolute maximum shear stress, as I indicated before, is the radius of the largest circle, which will be just the maximum stress minus the minimum normal stress divided by 2, and you have the associated average normal stresses. Okay, in the textbooks, or in some textbooks, and also in JC's notes, there's what they try to do is simplify things for students by trying to keep everything referred to in the 2D stress state. So they have various rules, I guess, for how to calculate the maximum shear stress. And they say if you have stress 1, or the two principal stresses have the same sign, then absolute maximum shear stress is calculated like this. Okay, so they're both over here. So it'll be so stress 1 will be here, and the normal stress in the z direction is 0, so the absolute maximum shear stress is this one. Or if they have opposite signs, so stress 1 is out here and stress 2 is negative, and stress in the z direction is 0, then the other two Mohrs circles occur on the inside of the original Mohrs circle that we drew from the 2D state of stress. Okay, so if you have opposite signs, then the absolute maximum shear stress is calculated like this. Okay, I prefer to just draw the 3D Mohrs circles all the time and just look at what the maximum shear stress is by looking at the biggest circle. Okay, so we're going to go through a couple of worked examples here. The detailed calculations, I'm not going to go through step by step. You'll see those in the tutorials. But hopefully this gives you an overview of the process, and also some examples that you can have a go at yourself, and then come back and look at how you're going. So with any of these examples that we show in the video lectures, I strongly suggest that you have a go at trying to do them yourself first. Just go step by step, see how far you get, and then stop. If you get stuck, come back to the video lecture and or just the notes and say, okay, right, now I see where I've gone wrong, or now I see where I'm stuck, and then carry on to the next bit without looking at the notes or the video. Okay, so in this example problem, we've got a pressure vessel, so similar to what I showed you in those pictures a couple of slides ago. We've got the hoop stress and the longitudinal stress, and you've got an answer here that we're going to be working towards. So have a go at trying to get to that yourself first, and then come back and follow along with the lecture if you need to. Okay, so there's our stress. Let's plot the 3 Mohrs circles. So start with our normal stress and shear stress axes. So to start with, we have our normal stress here and no shear stress. So that's going to be somewhere along this horizontal axis here. So just put that there. And then we've got normal stress in this direction. Okay, so that's going to be halfway along. So you can see stress in the hoop direction is twice the longitudinal stress. So we can draw our first Mohrs circle. Pretty easy. On the third direction, we have no stress, so a state of plane stress. But as I said before, just because there's no stress there doesn't mean we can ignore it. So that will be at the origin. No normal stress, no shear stress, so that gets plotted here. So now we have that, we can draw our other 2 Mohrs circles. So we'll have this one here, right, in this plane, right, between this axis and the normal axis out here, and our third Mohrs circle, which will be between this axis and our normal axis out here. Okay, so 32 and 0. Okay, so putting the numbers to that, so that was 32, this was 16. So the average stress will be 32 plus 16 divided by 2. The diameter here will be 32 minus 16, which is 16, divided by 2 is 8, gives us the radius. So that gives us the in-plane maximum shear stress. And then the radius of the biggest circle gives us our absolute maximum shear stress. Okay. And this will be oriented at 45 degrees to this horizontal direction. So again, this goes back to those pictures I showed you of the failed pressure vessels and pipes, where that 45 degree angle, 45 degree angle to the surface of the pipe was the failure plane. Okay, I'm starting to get a little bit croaky, so I'm going to have a drink. Sorry about that. Okay, so absolute maximum shear stress is this one, 16 megapascals. Average stress also 16 in this big circle, right? Not in the little one. Okay, so here noting that again, that the absolute maximum shear stress is not equal to the in-plane shear stress, and in fact, in this case, it's twice. All right, so if you don't calculate this absolute maximum shear stress and you do your strength-based design based on this one, you're going to be out by a factor of 2, okay, and not a conservative factor of 2. All right, you're going to under-design your component. So these results can be obtained by looking at the those rules that we looked at before. So, whoops, wrong way. So we had, what was it? I shouldn't do this, sorry. All right, these rules here. So stress 1 and stress 2 have the same sign, so we can get absolute maximum shear stress just from stress 1 over 2. Okay, and stress average. And then comparison with the in-plane shear, which I've already done for you. But you've got the numbers there. So next. Okay, so here we've got another example problem. So again, I strongly suggest that you have a go at doing the problem on your own first. This video is starting to get long. We're already up to nearly half an hour, so try and get through this. Okay, so have a go at doing this problem on your own first, and then come back and check your answers, or as you progress through the problem, get help as you need it. Okay, so here we've got our 2D stress element that we've calculated stresses using our stress analysis formulae, and we want to calculate the 3 principal planes and principal stresses and the maximum shear stress. Okay, so let's construct Mohrs circle. So we have stress in the x direction is 40 megapascals, and the shear stress is clockwise 20 megapascals, so that's plotted up here. And this one, stress 25, is here with the associated shear stress. That's going anti-clockwise, so that's plotted below. So we can calculate our average normal stress, 40 plus 25 divided by 2 gives us that. Calculate our radius, and then rotate around to get our principal stresses in the XY plane. Okay, so that's what we have here, and if we do those calculations using trigonometry or the Mohrs circle transformation equations, we get our principal stresses and principal orientation. So here we rotate from the x-axis around clockwise to theta, and on our actual element we rotate from x around clockwise theta p. Okay, and there's all the values there. So use this as a revision for last week's work. So now we want to go to the 3 principal planes. Yep. Okay, so from here, let's look at our stress in the z direction, which is again 0. So we can plot our Mohrs circle, our 3D Mohrs circles. Okay, so in the z direction it's 0. So again, we can plot that here. So between B and the z direction, we have our little Mohrs circle here, and then between the A axis and the z direction, we have our big Mohrs circle here. So our absolute maximum shear stress will be the radius of this big circle. Okay, so this stress A here we calculated previously to be 53.9. Okay, so the this radius here of the big circle would be half that, so 26.95. Okay, so as I've said here, and I think I said this earlier, don't worry too much about whether you can work out where the absolute maximum shear plane is and its orientation. The most important thing to know is to calculate this absolute maximum shear stress, which, as you've seen in this example and the previous one, may be much bigger than the in-plane maximum shear stress. Okay, so that's the end of this lecture. The next one we'll look at predicting failure, or looking at failure criteria for ductile and brittle materials, predicting failure using the yield criteria, and introducing these into strength-based design and looking at design factors. Okay, so thanks for sticking with me till the end. Hopefully that was helpful for you and I didn't confuse you too much with the SOLIDWORKS models and the different planes for the maximum shear stress. So make sure you have a go at those problems, and yeah, I'll catch you in the next video. Take care. See ya.